So where we're picking up is this here. What we want to do for these is rewrite in terms of x. So we want to rewrite it in terms of a single x, not 3x. And we can do that using some of our sum or difference properties. And for the most part, we're going to be using sum properties because we don't want to write it as a difference, because a difference is just going to make it bigger and give us a negative x. Now what we can say is sine of 3x is the same as sine of 2x plus x. Now this will mean we're going to have to do multiple steps. Right, okay, I see what we're doing. Multiple steps. Now our sum formula for sine, I had the reference pages in the correct order, and make this even better, is the same as sine of alpha, which is sine of 2x, cosine of beta, so cosine of x, plus cosine of alpha, sine of beta. And for us here, alpha is 2x, beta is x. Now, luckily for us, we did go with having 3x inside of the trigonometric functions. And we do have 2 now that have just x. However, we also have 2 now that have 2x. So we've kind of taken a step forward and a step backwards at the same time. Or it might feel like 2 steps backwards in some cases. But luckily for us, sine of 2x, cosine of 2x are both double angle formulas. Now sine of 2x has exactly one equation, and it's 2 sine of x cosine of x. That's the only equation we have. Sine of 2 theta is equal to 2 sine of theta cosine theta. So in our terms, we have x, so sine of 2x equals 2 sine of x cosine of x. Plus. We have many different options we could go for this next part here. Well, I'm just going to pick the top one. I'm going to say cosine squared of x minus because we have this version here, cosine of 2x is equal to cosine squared of x minus sine squared of x. We also have cosine of 2x is equal to 2 cosine squared of x minus 1. And we also have cosine of 2x is equal to 1 minus 2 sine squared of x. So we have 3 different options we could pick. I just went on and picked the first one. Questions on this here? Now at this point here, we can distribute our cosine here, telling us that we have 2 sine of x cosine squared of x plus. Here we can distribute the sine. Cosine squared of x sine of x minus sine cubed of x. Now we can simplify this a little bit. Which I'll finish writing. Our first 2 terms, 2 sine of x cosine squared of x plus cosine squared of x sine of x. Those, for all case and purposes, are the same, yes? So really, we can combine these here, giving us 3 cosine squared of x sine of x minus sine cubed of x. And I believe that's as simplified as it gets. Questions on this here? Questions on anything we're done for this one? Let's make sure. Rewrite in terms of x. We have this here. Now, some of them might give you a bit more information, like it wants it in terms of sine of x, and we do things a little different. So we do have this here, because if we wanted to, we could have rewritten this in terms of sine or purely in terms of cosine. But that's about it. Because if we wanted to write this purely in terms of sine, because that's what the book has for the most part, or especially for this problem here, the only difference is, is that this essentially is almost completely in terms of sine, but you don't have to write this down. I don't know what that is. But cosine squared of x is the same as 1 minus sine squared of x. And we can plug that in. Now we can distribute, telling us that we have sine of x minus sine squared of x minus sine cubed, this should be cubed, of x. We distribute the 3, telling us that we have 3 sine of x minus 3 sine cubed of x minus sine cubed of x. So I say we have 3 sine of x minus 4 sine cubed of x. Same thing. This is just in terms of sine. This is purely just getting it in terms of x. I don't think we'll have one specifically stating one over the other, but it is possible to do this. So this one here, we'll do it the other way. We'll rewrite it completely in terms of cosine of x, which for the most part isn't too bad, because we'll start off exactly like we did the last one. We'll start off with a sum. Now the reason we're starting off with a sum is because 3 is not a multiple of 2, so we can't use the double angle formula. Because if it had been 4, 4x, well, I can rewrite 4x as 2 times 2x and just apply that 2 to our double angle formula. Because we're treating this almost as the x and applying that 2x throughout, and then we can do it again. But we don't have that. We just have this here. So to get 3x to be a multiple of 2x and x, we use the sum formula, which tells us that we have cosine of 2x cosine of x minus sine of 2x sine of x. Now we do want to get this completely in terms of sine or just cosine. So the first one I'm going to look at is this side over here, because no matter how we look at it, sine of 2x has one option for the double angle formula, which is just 2 cosine of x sine of x. That's the only one we got. Now the other side, cosine of 2x, we have several. We've got cosine squared minus sine squared. We've got 2 cosine minus 1 and 1 minus 2 sine squared. So our double angle, cosine squared minus sine squared, 2 cosine squared minus 1 and 1 minus 2 sine squared. Well, if we want this completely in terms of cosine, I'm going to lead towards cosine squared of x minus, 2 cosine squared of x minus 1 times cosine of x. Because if we want it purely in terms of cosine, we're going to go this route because I don't have sine. I'm not adding any additional sine functions into the equation. Now on this side here, we would distribute the cosine of x. So we have 2 cosine cubed of x minus cosine of x minus. Now I dropped the parentheses on the first one because we're multiplying by a positive cosine. Sine's not changing, we have this here. We leave the parentheses around the last one because of this minus in the middle, which we will have to apply later on. Now I can distribute sine. So we have 2 cosine of x times sine squared of x. Now, oddly enough, we do have one single term, so we really didn't need the parentheses. Cosine cubed of x minus cosine of x minus 2 cosine of x times. So we can drop the parentheses, but as I said earlier, we're going to try to rewrite this completely in terms of cosine. So we need to switch out the sine squared. Well, according to our Pythagorean identities, one of them is our sine squared plus cosine squared equals 1. Well, if we work it out to get sine squared by itself, sine squared is also equal to 1 minus cosine squared of x. So this does work out in our favor because now I have an entire equation that is all in terms of cosine. So the last thing we really need to do is simplify. So we'll distribute the negative 2 cosine of x, which tells us that we have 2 cosine cubed of x minus cosine of x. Negative 2 cosine of x times 1 is negative 2 cosine of x. We do have some like terms here. Negative 2 cosine of x times negative cosine squared. We'll have plus 2, and our cosine times cosine squared is cosine cubed of x. Nicely enough, we do have like terms. 2 cosine cubed of x plus 2 cosine cubed of x is 4 cosine cubed of x. Negative cosine of x minus 2 cosine of x is minus 3 cosine of x. Questions on this here? And again, what we're saying, all in all, is that cosine of 3x should be the same as this here. Well, that seems very odd, considering we're looking at a cosine function. Zoom 7. Have this here. And we said that we got the same thing from 4 cosine of x to the third minus 3 cosine of x. Yes? So if these are the exact same, fingers crossed they are, the blue line should be covered up with the red. And it is indeed. So they are the exact same function. And if we looked at the table, all the y values that we get for any x is the exact same. So they are indeed the same function. Questions on this here? All right. Power reducing. Sine to the fourth. We want to reduce it so that the power for this is 1. We don't want to have any powers left here. Now, there are set equations for this. And since we're starting off with sine, our power reducing form for sine is that sine squared of theta is equal to fraction to 1 minus cosine of 2 theta over 2. So that's our power reducing form. But we don't have square, we have fourth power. So the way we have to look at this is sine squared of x squared, almost. We're looking at it as a square squared. Yep. So it seems like we're going to be affecting the square. Well, not really. What we're doing is now going to be replacing the one inside the parentheses. Because our 1 minus, or our sine squared of x, try not to scroll, inside here, this will be replaced with our 1 minus cosine of 2 theta over 2. Because sine of squared of x is 1 minus cosine of 2, well, if I write the correct term, x here. We good with this so far? Because I just rewrote it in a form that works, so since we can't do sine to the fourth, because we just have sine squared, we rewrote it as sine squared of x, whole term squared. I can replace the sine squared of x with our equation, and we get this here. Now, I can't leave it as this, because we do have a power, and really this is telling us that we have 1 minus cosine of 2x over 2 times itself. Over 2. Now, whenever we multiply two fractions, we multiply straight across. So the denominator, 2 times 2 is 4. The numerator, our 1 times 1 is 1. 1 times cosine of negative cosine of 2x is negative cosine of 2x. Negative cosine of 2x minus negative cosine of 2x times negative 1 is negative cosine of 2x. And lastly, negative cosine of 2x times negative cosine of 2x. Negative negative makes it plus. We have cosine squared of 2x. Now, I'm going to do two things. One, I'm going to combine like terms. So we're going to have 1 minus 2 cosine of 2x plus cosine squared of 2x. We're good with that there. I am also going to pull out that 4 is we're really saying we're dividing everything by 4, which is the same as saying that we're multiplying this all by what? Because it's not 4, because 4 has to go on bottom, yes? So it's the same as multiplying it by 1/4. Does that make sense? So I pull that fraction out because now we're not looking at so much the fractions. It makes it a little bit easier to work with because after doing that, did we get rid of all the squares? Kind of. It's now not in a 4th power, we're now just in a 2. Well, now I'm going to go back to power reduction because cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. So over here we'll still have our 1/4. We still have the 1 minus 2 cosine of 2x. Now we need to replace cosine of 2x, cosine squared of 2x with power reduction. So we will have a fraction. We'll have a fraction. We'll have a denominator of 2. Other parentheses. We do have the 1. We do have the plus cosine. But what's inside is not going to be 2x. Because when we started this, we said sine to the 4th gave us 1 minus cosine of 2x, yes? The original variable inside the parentheses was just x, yes? What is it this time? 2x. So our theta in the standard equation is now 2x. In the formula, it goes from theta to 2 theta. So we're going from now 2x to 2 times 2x, which is 4x. We have to multiply by 2. Now we're essentially done almost, but that division of 2, I'm going to pull or essentially divide everything by 1/2 to pull that out. So out front, we do have the 1/4, and we do have the 1/2. But what kind of makes things tricky is the other 2, because the last one is going to become 1 plus cosine of 4x. But I have to divide the 1 by 1/2 to factor it out. Let's see what happens. 1 over 1/2 is 2, because if I multiply the 2 by 1/2 to get back to 1, it has to be 2. So that means that's 2 minus, which means I'm also dividing the 2 cosine of 2x by 1/2, which actually gives us minus 4 cosine of 2x. Does that make sense what we did? Yes? Okay. Last thing we can do is start simplifying, combining like terms. Well, 1/2 times 1/4 is 1/8. Here, our 2 plus 1 is 3 minus 4 cosine of 2x plus cosine of 4x. Questions on this here? Luckily, this is not as bad as to the 8th, or because we'd have to repeat the process a few more times. Questions on any of this here? Rewrite tangent to the 4th in terms of first powers of cosine of multiple angles. And again, with most of these here rewrites, I'm going back to our formulas. Because tangent squared of x is equal to 1 minus cosine of 2x over 1 minus sine of 2x. And we're going to do the exact same thing that we did last time if I can write the formula correctly. One minus cosine of 2x over 1 plus cosine of 2x is the correct formula. We're going to do the exact same thing we did on the last one, essentially. There's going to be a few different steps because we're talking about tangent instead of cosine or sine, but we do get the same kind of process. So that means for us that we're going to replace our tangent squared with 1 minus cosine of 2x over 1 plus cosine of 2x, and we have the whole thing squared. So to simplify this, we have to multiply the whole thing by itself. So we'll do the numerator first. Our 1 times 1 is 1. 1 times negative cosine of 2x is negative cosine of 2x. Negative cosine of 2x times 1, negative cosine of 2x. And negative cosine of x times negative cosine of x is plus cosine squared of 2x. The denominator, 1 times 1 gives us 1. 1 times cosine of 2x is plus cosine of 2x. Cosine of 2x times 1 is plus cosine of 2x. And lastly, cosine of 2x times cosine of 2x is plus cosine squared of 2x. Apparently, we're going to scroll. Now we can combine like terms, so we have 1 minus 2 cosine of 2x plus cosine squared of 2x. And on the bottom, we have 1 plus 2 cosine of 2x plus cosine squared of 2x. Questions on this here? Now it'd be very nice if we could just cross out the cosine squared of 2x on top and bottom and be done, but that isn't how this works, unfortunately. Because as we saw in the last one, cosine squared of theta is equal to 1 plus cosine of 2 theta over 2, or in our case, x. We're going to do it again. And again, just like the last one, we have 4x. Because we're replacing cosine squared of 2x with its form, which would be 1 plus cosine of 4x, because we have to multiply our 2x by 2 to get here. Questions on this here? Questions on anything we've done so far? Anything that seems odd, weird, strange? Now there's one glaring issue with this. We have a fraction and a fraction. So looking at just our 1 plus 4, or 1 plus cosine of 4x over 2, what could I multiply that by to get the denominator to become 1? 2, yes? Because if I multiplied the entire numerator by 2, that would simplify that. Well, the same thing is true in the denominator. So what's nice is I can multiply the entire numerator and entire denominator by 2. And there's a reason we can do it. What is 2 over 2? So really, I'm just multiplying the entire equation by, it's just a fancy version of 1. But I have to do it to all 3 terms on top. Now, page. Our 1 multiplied 2 becomes 2. Our 2 cosine of 2x becomes 4 cosine of 2x plus, well, this 2 and that 2 are gone, leaving us with 1 plus cosine of 4x. And the reason this is nice is now the entire numerator has no powers. And that's our goal. Now the denominator, we can do the exact same thing. Multiply everything by 2. So we'd have 2 plus 4 cosine of 2x plus, well, this 2 is gone, 1 plus cosine of 4x. Last step, combine like terms. 3 minus 4 cosine of 2x plus cosine of 4x all over 3 plus 4 cosine of 2x plus cosine of 4x. And this, for some reason, is supposed to be a better version than tangent to the fourth of x. I'll go back to that in a second. Of x to the fourth. There's our tangent of x to the fourth. Alpha y equals, enter, 2, not 2, it was 3 plus, make sure I'm getting this, minus 2 cosine of 2x plus 3 minus 4 cosine of 2x plus cosine of 4x. Okay, 3, I got that completely wrong, minus 4 cosine of 2x plus cosine of 4x all over 3 plus 4 cosine of 2x plus cosine of 4x. Yep, covered it right up. Like it should. If we look at the table, all the values we see here are the exact same. That's telling us that this is indeed the same as, almost wrote the wrong thing, tangent to the fourth of x and that's it. Questions on this here? Simplicity wise, there's no way that we could ever say this is more simpler than I'm just saying tangent to the fourth of x. But there you have it. Questions on this here? How much we have left? Wow. Let's get through at least one or two more. Now, sine of 105 degrees. We want to find the exact value using our half angle formulas. Or really, we're wanting to use the unit circle because 105 degrees is not on the unit circle. But if we take 105 and multiply it by 2, we get 210 degrees. 210 degrees is on the unit circle. So the way we can find the exact value using half angle formulas is that we say sine of 105 degrees is the same as sine of 210 degrees over 2. Now the reason we're doing this is because sine of u over 2, or we can say theta, is equal to, I'm going to just stick with theta, is equal to plus or minus the square root of 1 minus cosine of theta over 2. Now the plus or minus does come into play, and it's more dependent on which quadrant it lies. So the sine of theta over 2 and cosine of theta over 2 depends on which quadrant, on the quadrant in which theta over 2 lies. So if we think of theta over 2 is 210 degrees over 2. Or really, we're looking at 105. I'm going to do a little one. Because 0, 90, 180, 270, then we get back to 360. Luckily for us, 105 is between 0 and 360. And it's over here in the second quadrant. And for us, we're talking about sine. Sine is positive in the second quadrant. So that means the formula that we use when we plug this in, we're going to look at the positive version of this here, not the negative. If we had been talking about the third or fourth quadrants, it would have been negative. So for this here, we have the positive square root over 2. Now, 1 minus. So we have cosine of theta. And for our formula, we have sine of theta over 2. Well, our theta value is 210 degrees. And again, they want us to find the exact value of this here equals, well, cosine of 210 degrees, look at the unit circle, is negative square root 3 over 2. Now we need to do some simplifying. Our negative is going to make a plus. So we have 1 plus square root of 3 over 2 over 2. Now we can't have a fraction inside of a fraction inside of a radical. Well, we can't have a fraction in a radical and be simplified, let alone having a fraction inside of a fraction inside of a radical. But the first thing to do is going to be to simplify our fraction inside of a fraction. So we can think of it as division. Because we're saying the numerator is being divided by the denominator, that's what a fraction is. And to simplify this, we're really saying that we have 1 plus square root of 3 over 2 being multiplied by 1/2. Because to divide fractions, we change it from division to multiplication and flip our second term. So we multiply both of these by 1/2. Which actually gets us here. Well, at this point, we'll need to add these together. Should have done that from the beginning. But since we started doing this by hand, we're going to finish going by hand. 1/2. To be able to add, we need both of these to be in fourths. It's the only way to add two fractions is for the denominators to be the. And to turn 1/2 into fourths, it would be 2/4. So we have 2 plus the square root of 3 over 4. So we've gotten one of the issues fixed, because now we don't have a fraction in a radical. We just have a fraction in a radical. And to simplify it, one of the properties of radicals is that we can take the square root of the numerator over the square root of the denominator. And this works out nicely, because the square root of 4 is indeed 2. And according to the formula, the square root of 105 is this here. The square root of 2 plus the square root of 3 over 2. And it's positive because sine of theta is positive in the second quadrant. And we have this here. Remark. Use your calculator to verify the results to obtain epsilon equal 5. This is evident. This is evaluate sine of 105 and square root of 2 plus square root of 3 over 2. Note that both are the approximate same value. Now, one thing that is interesting, mode. Actually, degrees is what we need. Second quit. Sine of 105 is this here. There is a way to get from that to here. It's a puzzle I've attempted a few times to try to figure out, but either of these are the exact same value. Interestingly enough, second square root of 2 plus second square root 3 over 2 is this here. And if we approximate this, it's the exact same thing. They are the same value. It's something to deal with our squares or factoring to get that radical out. But for the most part, it's not something that's hugely important. So they are the same.